Alright, this is example 1 in module 7. We have a positively charged particle that's traveling along a straight line in the positive x direction. I have a coordinate system drawn here for reference. And it is in a uniform electric field that points in the negative y direction. There's an unknown magnetic field that we need to determine the direction and magnitude of. So if there was no magnetic field, of course this particle would be accelerated in the direction of the electric field, and it wouldn't travel along a straight line. So the magnetic field exerts a force on the particle that keeps it in a straight line. So we know that the sum of the forces that are exerted on the particle has to be 0 since it travels along a straight line. So we need to first figure out what direction the magnetic force needs to point, and from that we can determine what direction the magnetic field has to point. So let's consider a free body diagram for the particle. The particle is positively charged, so it's going to have a force that is in the direction of the electric field exerted on it. That's going to be the electric force. The only way to cancel the force that points straight down is to have another force that points straight up. This is going to be the magnetic force. Now, the magnetic force does not point in the direction of the magnetic field. We have to use the right-hand rule to determine what direction the magnetic field points. If we had a magnetic field with a charged particle traveling through it, the way that we would determine the direction of the force is to point our thumb in the direction of the velocity vector, point our fingers in the direction of the magnetic field vector, and then our palm would point in the direction of the force exerted on a positive charge. If the charge happened to be negative, then we would have to switch the direction. In this case, we know the direction of the force, we know the direction of the velocity vector, we don't know what the direction of the magnetic field is. So to apply the right-hand rule, we're going to point our thumb in the direction of the velocity vector, so that's straight to the right. And then I need to find the direction that I have to point my fingers that would result in my palm pointing up. So if I point my thumb to the right and I point my palm up, my fingers point into the board. So the magnetic field has to point into the board. All right, now let's determine what the magnitude of that magnetic field is. Well, we can apply Newton's second law here, which says that the sum of all forces exerted on a particle is going to be equal to its mass times the acceleration. Now we know that the acceleration is 0 here because it travels along a straight line. There's only two forces involved. We have a magnetic force that points up, so I will write positive magnetic force. We have an electric force that points down, so I'll write negative electric force. These two, well, if we take the magnitude of the magnetic force and subtract the magnitude of the electric force, that has to give us 0. For the electric force, we know that the force exerted on a charged particle is just Q times the electric field magnitude. So this is the magnitude of the electric force. We don't know what this charge Q is yet, but let's just write down Q as a placeholder. It's going to cancel out, so it won't end up in our final answer. If we got to an answer that had this Q in it, then we would know that there was some other piece of information that we would need to bring in order to remove the Q from the solution. The magnetic force magnitude is given as QVB sine theta, and this angle theta is the angle between the velocity vector and the magnetic field vector. Now we're told to assume that the velocity vector and the magnetic field vector are perpendicular to each other. So theta is equal to 90 degrees, and sine of theta will be equal to 1. Alright, so sum of all forces is equal to 0. We have a magnetic force minus an electric force. The electric field is given, the velocity is given. So we know what the electric field magnitude is, we know what the velocity magnitude is. We don't know what this charge Q is, but the charge Q is in both terms, so that means that it's going to cancel. All right, so what we want to do is solve for B. So I'm going to write QVB is equal to QE, which means that V times the magnetic field strength is equal to the electric field strength. So the magnetic field then is the electric field over the velocity. Now, if we wanted to write this as a vector, because this is just the magnitude, we already know what the direction of the magnetic field points. So we would write down the magnetic field as a vector is equal to the electric field strength over the magnitude of the velocity, and it points into the board, which would be the negative z direction. So I'm going to write a z hat and put a negative sign there. That would be the magnetic field vector. This is called a velocity selector because it's used to select particles with a given velocity. If I increase the velocity here by a little bit, then that will change what the magnetic force excuse me, that will change what the magnetic force is, and I won't get a particle traveling along a straight line. So only particles with a specific velocity will travel along straight lines.